Hello and welcome to the Unit 4 podcast on Section 11.1, Measuring Matter. I'm Mr. Sakaguchi.
And I am Mr. Lin.
And here we go. Today we're going to be talking about counting particles, and when we're trying to count particles, the unit that we're going to be working with is something known as the mole. It basically represents the number of particles in 12 grams of carbon-12. Carbon-12 is an isotope of carbon.
So when we're talking about particles and representative particles, what that means collectively are individual units such as atoms, molecules, formula units, or ions. So each of those individual pieces collectively. So that's just a catch-all phrase. Since all of these particles are so tiny, we're going to need a way to reorganize the amount of them so it's easier for us to count, and that's where the mole comes in. And 1 mole of any substance is equal to 6.02 times 10 to the 23rd particles. That's kind of like saying a dozen is 12 pieces. So instead of saying 6.02 times 10 to the 23rd all the time, we use 1 mole.
And sometimes we refer to 6.02 times 10 to the 23rd as Avogadro's number. So what do we do with this number? Well, before we go into that, I want to introduce a mathematical concept known as dimensional analysis. Basically, the idea behind dimensional analysis is unit cancellation. Now, most of you guys in algebra know that if I have x over x, they would factor down to 1. Similarly, what we're going to do is we're going to multiply by fractions in such a way where variables like meters or grams will cancel out as well. And that'll allow us to move from one unit of measure to another one. And if you think about it, when we're done with all this mole stuff, you're going to realize that we're essentially just converting units of measure.
Right. So this is just unit conversion, and this is just adding one more unit ratio. Just like 12 inches is in a foot, or a dozen is 12 pieces. This is just one more thing to know. It's not, and the mathematics is the same throughout all of them.
So we're going to use how many seconds there are in 2.56 years as a way to kind of explain how dimensional analysis works. So let's say we were going to do this. Well, we would start with our given over 1. So in this case, since there's only 1 unit, this is what we'd start off with, and see how it's over 1. Now the goal of our next factor is to cancel out units of years. Now I don't know how many seconds there are in a year, but I know how many days approximately there are in a year. So I add that to my next fraction.
So as you can see, 1 year has 365 days. We all know this. Now the reason that this ratio is written as 365 days over 1 year is so that you can get your year's unit to cross-cancel each other, to cancel each other out when you multiply, so that when you have year over year, they cancel each other out and you're left with just 1 in the denominator, and the only unit remaining would be your days.
So here are the units canceling out. Whenever you have the units above in the numerator and then the denominator, they will cancel out. Now if we stop right here, our final answer would be in days, but we want seconds. I don't know how many seconds there are in a day, but I do know how many hours there are in a day. So there are 24 hours in a day, and again 24 hours goes on top so that days can cancel. And if I stop here, my final answer would be in hours, but I don't want that. I do know how many minutes there are in an hour, and now hours cancels out, and I know how many seconds there are in a minute, so now minutes cancel out. Once we're done here, what we would do is we'd multiply across the numerator, we would multiply across the denominator. If there were numbers in the numerator and the denominator, we would actually divide. In this case, we don't have to because everything in the denominator happens to be 1. And when we multiply everything out, we get a very large number, which makes sense in terms of seconds. We're going to utilize the same strategy with our mole conversions.
So here we are with the first process of how to convert from the mole that you guys just learned about to convert them to particles, again representing individual pieces like atoms and molecules. Always start with your given unit or given amount over 1. Okay? That way when you set it up, it's nice and neat. Next up, using the chart on the right-hand side, you can see the ratios of 6.02 times 10 to the 23rd representative particles to a mole, and it can go both ways. The question is which one to use. When you're going from In this situation, first we're going from moles to particles. We're starting down here and we're moving our way up. We're going to wind up needing to use the ratio of Avogadro's number over 1 mole, just to start out with.
So using this mole rule kind of helps you figure out what your multiplier are given by. So if we're going up from moles to representative particles, that better mean that your given has moles in its units. That way moles can cancel. So whatever's on the bottom in this case will cancel out. If we're going from representative particles to moles, that means that you should have some unit of representative particles in your given over 1. And because if things don't cancel and you end up with square moles or something like that, then you know you're making mistakes. So here's an example of going from moles to particles. Let's say I asked you to calculate the number of molecules in 11.4 moles of water. Now remember, molecule is a specific representation of representative particles. And we're given 11.4 moles of water. So my given is in terms of moles. So I'm going from moles to molecules, which is a representative particle. So what I've highlighted here in red and in bold represents the direction we're going down the mole road and what we're going to have to multiply our given by.
So the fact that we have moles as our starting unit in the given problem tells us that's what we need to look for in the denominator. That's how we can choose between the two.
So we start with our given over 1 and we multiply by our mole road factor. Notice how we have moles over moles, which cancels. And we multiply 11.4 times 6.02 times 10 to the 23rd. You end up with 6.86 times 10 to the 24th molecules of water. Now it's very important for you guys, if you haven't already gotten your scientific calculator, to make sure you get one.
And to learn how to use it.
And actually learn how to properly use it, of course. This is one of the #1 mistakes where students mess up these problems, that they understand the concept, but they didn't learn how to properly enter in scientific notation. So make sure you know how, or one of your teacher shows you how to do it.
Also be aware of what's going on with the exponents. Some people might get a little confused by that, but when you have 11.4 times 6.02, you wind up with 68.6, but that's not scientific notation. So we had to move that decimal over from between the 8 and the 6 to one more position over to the left. And as a result, the exponent increases to 24. So be sure you're aware of that kind of mathematics going on.
And if you have a scientific calculator, it'll do it for you.
Right.
So more reasons to buy it. And I think that's it.
Yep. Oh no, we have to do it the other way around.
So now we're not done. We're going to go in the opposite direction. We're going to go from
Just kidding.
Particles to moles. So let's say I asked you to find the number of moles in 5.35 times 10 to the 24th formula units of NaCl. Formula units is a representative particle specific for an ionic compound.
Right.
So now we're going to go from representative particles to moles, and now we're going to multiply by 1 mole over Avogadro's number.
Again, because we're dealing with formula units or representative particles, so that's what we need to have in the denominator of the ratio.
So we have our 5.35 times 10 to the 24th formula units, and we multiply by our factor. So notice we have formula units on top and bottom, which cancels, leaving us with the unit of moles, which is exactly what we want to find. And then in this case, we have to divide, and we end up with 8.89 moles of NaCl.
Again, this is where a scientific calculator can really come in handy, because you're dealing with large numbers here.
By the calculator.
Yes, please.
And that's it. This time I think it's really it.